I want you to think about the last time you pulled out your phone and used an AI chatbot, or, maybe generated an image.
Yeah, it's become such a casual thing for all of us, right?
Exactly. I mean, you type in a quick prompt, maybe you're asking for a complex legal summary, or, I don't know, generating a picture of a cat riding a skateboard on Mars.
The classics.
Right. And you hit enter, and almost instantaneously, the result just materializes on your screen.
Like magic.
Like magic. It feels completely weightless.
Right.
We even have this overarching, almost poetic metaphor that we use for all of this digital infrastructure.
The cloud.
The cloud. But as we are going to explore today in this deep dive through some frankly terrifying data sets, the cloud is just a complete misnomer.
It really is. It's probably the biggest tech illusion we have right now.
Yeah, because it is not some ethereal mist floating above us. It is a massive, roaring facility made of concrete and steel. And more than anything else, it is incredibly, staggeringly thirsty.
It is the ultimate sleight of hand of the modern tech era. I mean, we are completely mesmerized by the output, right? The brilliant text generation, the photorealistic images, the code being written in seconds.
Right, so distracting.
Exactly. And because of that distraction, we are entirely ignoring the physical intake required to make that happen.
The actual physical resources.
Yes, the physical infrastructure that is demanding natural resources on a scale that is honestly genuinely difficult to comprehend until you start looking at the hard thermodynamics.
Okay, let's unpack this. Because we need to completely shatter this illusion of the digital cloud, right?
Okay.
We need to step through the front doors into the actual physical reality of AI infrastructure.
I think that's the only way to really grasp what's happening.
Because anyone listening knows that computing generates thermal exhaust. I mean, if you run a heavy program, you can literally feel your laptop get hot on your legs.
Oh, absolutely.
But we're not talking about a gaming rigs fan spitting up here. We are talking about thermal energy on an industrial, almost geological scale.
Yeah, the scale is just totally different.
So to understand why this thirst exists, I feel like we have to start the very foundation. What exactly is an AI data center physically doing that makes it so fundamentally different from, the warehouse that hosts standard websites or email servers?
Well, the distinction really comes down to the architecture of the silicon itself.
Okay, break that down for me.
So, a traditional data center, the kind that has basically been the backbone of the internet for the last 2 decades, is essentially a large warehouse filled with standard servers. And those rely on CPUs, right? Central processing units.
Like what we have in our desktop computers.
Exactly. And CPUs are fantastic at sequential processing. They handle basic database queries, they route web traffic, they manage your email, one thing after another, very efficiently.
Right.
But AI workloads, especially when we're talking about the training of these massive large language models, they cannot function efficiently on sequential processing.
Because there's just too much data.
Yeah, they require parallel processing. They need to perform like millions of incredibly complex mathematical calculations simultaneously, all at the exact same time.
So the industry had to pivot the hardware.
They did. They pivoted to GPUs, graphics processing units, and specialized AI accelerators.
Okay, so they swapped the chips. Why does that change the heat output so drastically?
Because from a physical engineering standpoint, when you shift from a traditional CPU to an array of highly advanced GPUs, you are dramatically increasing what we call the transistor density.
Transistor density, meaning they're just packing more stuff into the same space.
Exactly. You are packing billions of microscopic electrical switches into a tiny, tiny square of silicon.
Wow.
And when you run those chips at near maximum capacity, 24 hours a day, 7 days a week, literally pushing electrical current through billions of microscopic gates, the physical electrical resistance generates an extraordinary amount of heat.
Okay, I have to push back here, or at least play devil's advocate for a second.
Sure.
Moore's law, or at least the general spirit of it, suggests that as chips get smaller, they become more power efficient.
That's the common assumption, yeah.
And tech companies are notoriously obsessed with efficiency. So I find it hard to believe they haven't engineered a way to get more compute out of less power, which should theoretically mean less heat.
I mean, it makes logical sense, but it runs into the brick wall of something called Dennard scaling. And that essentially broke down over a decade ago.
Oh, really? How so?
Well, While we absolutely can pack more transistors into a smaller space, the power density, meaning the amount of heat generated per square millimeter of silicon, is no longer scaling down proportionally.
So smaller doesn't mean cooler anymore.
Not at all. We are dealing with something called thermal design power, or TDP. A modern high-end AI chip can have a TDP of over 700 watts.
700 watts for one chip.
Yeah. Imagine the intense heat of a small industrial space heater, but concentrated into an object the size of a drink coaster.
That is insane.
Now take thousands of those coaster-sized space heaters, stack them into metal server racks, and line up hundreds of those racks in a single enclosed room. The thermal energy being released is just astronomical.
So what happens if that thermal energy isn't immediately removed? I mean, we aren't just talking about the computer running a little slower to cool itself down, are we?
Oh no, we are talking about catastrophic, multi-million-dollar physical destruction.
Like they would literally melt.
Quite literally. If the heat isn't extracted continuously, the silicon will degrade, it will warp, and it will melt. The delicate microscopic pathways inside the chip will just be completely destroyed.
Wow.
It's not just a matter of performance throttling, It is an existential threat to the hardware itself. If the cooling system in a hyperscale AI data center fails, the entire facility has to grind to a halt within minutes just to prevent the hardware from immolating itself.
Okay, so you have a multi-billion-dollar investment generating temperatures that would destroy itself if left unchecked. You absolutely have to move that heat away from the silicon and out of the building. And I guess that brings us directly to the core mechanism of our deep dive today, which is water.
Yes, water is the key to all of this.
Because according to the reports we're looking at, water isn't just some supplementary tool. It is the central artery of the entire AI boom.
That's a great way to put it.
And it's not just a single point of consumption, right?
Yeah.
The sources detail a three-pronged thirst, meaning AI infrastructure consumes water through direct cooling, electricity generation, and semiconductor manufacturing.
Yeah, it hits the water supply from three completely different angles.
Let's look at the mechanics of direct cooling first, because this is what is actually happening on site at the data center.
Right, the most visible part.
Yeah. But why water? Why not just blow really cold air over the machines like we do with traditional server rooms?
Because the physics of heat transfer simply won't allow it at this extreme density. You have to look at the specific heat capacity of the cooling medium. Water is incredibly dense compared to air. In fact, volumetrically, water holds roughly 4,000 times more heat than the equivalent volume of air.
4,000 times? That's massive.
It has an incredibly high thermal conductivity. If you tried to cool a massive, high-density AI cluster with just air, you would need industrial fans blowing constantly at hurricane speeds.
Which I assume uses a ton of power.
A tremendous amount of electricity. Plus, it generates deafening noise, and honestly, it still struggles to pull the heat away fast enough from those dense GPU clusters. Water is literally the only medium cheap enough and effective enough to act as the heat sink.
Okay, I understand that water is a great coolant, but surely these tech companies with essentially infinite engineering budgets aren't just hooking up a municipal water line, running it over the servers, and dumping it straight down a drain.
You would hope not.
Right. I mean, they must have sophisticated closed-loop systems where they just chill and reuse the exact same water indefinitely, right?
You'd think so, but the physics of heat rejection, combined with basic corporate economics, makes that closed-loop ideal incredibly rare for large-scale facilities.
Really? Why is that?
Let me explain the mechanics of what they are actually doing, which is primarily evaporative cooling.
Okay, evaporative.
Yeah, a closed-loop system simply moves the heat from the server to a liquid. But you still have to get the heat out of that liquid eventually, right?
The heat has to go somewhere.
To do that without losing any water requires massive, power-hungry mechanical chillers, basically giant industrial refrigerators. And that uses an enormous amount of electricity.
I see. So to save on their massive electricity bills, they just evaporate the water instead.
Precisely. They use cooling towers. The heated water from the data floor is pumped outside to a big cooling tower. There, it is sprayed over a specialized material called fill media.
What does that do?
It spreads the water out to maximize its surface area. And at the same time, massive fans pull outside air through the falling water. Now, here is the crucial thermodynamic mechanism. As the air meets the water, a small percentage of that water undergoes a phase change. It turns from a liquid into a vapor.
So this is exactly how human sweat works.
It is the exact same mechanism. the latent heat of vaporization. When water changes from a liquid to a gas, it absorbs a massive amount of thermal energy.
Right, which cools you down.
Exactly. By evaporating just a small fraction of the water, it dramatically drops the temperature of the remaining water, which is then pumped back inside to cool the servers all over again.
But the water that turned to vapor, that's just gone.
It is vented out into the atmosphere as exhaust.
Yeah.
It is permanently consumed and removed from the local watershed.
Wow.
And because they are constantly evaporating water to achieve this cooling effect, they have to constantly pump fresh municipal water into the system to make up for the loss.
And the scale of this evaporative loss is what makes these reports so alarming. The data we're looking at shows that a single large data center can consume up to 5 million gallons of water a day.
Staggering.
I want to convert that for our global listeners because it's vital. That is approximately 19 million liters of water every single day.
And to contextualize that volume,
Yeah.
19 million liters is roughly equivalent to the daily water usage of an entire small to mid-sized town.
Just gone, evaporated.
Yeah, that is just one facility drinking a town's worth of water every 24 hours merely to maintain the thermal equilibrium of its computers.
That is only prong number one. That's just the water evaporating directly out of the top of the building. Prong number two of this thirst is electricity generation.
Right, the indirect usage.
Yeah, this is entirely indirect, and yet the report suggests the water footprint here is sometimes even larger than the direct cooling. How does drawing power from the electrical grid suddenly equate to massive water consumption?
Well, we have to trace the electricity back to its actual physical source.
Right.
AI data centers are power-hungry behemoths. They require continuous, massive baseload electricity.
Right.
And how do we generate the vast majority of our electricity globally? Through thermal power plants. That includes coal, natural gas, and nuclear plants.
And the fundamental mechanism of a thermal power plant really hasn't changed in over a century, has it? You basically just heat something up to boil water.
That's it. You boil water to create high-pressure steam. That high-pressure steam is forced through a turbine, physically spinning a generator to create electricity.
Okay, but where is the water loss happening there?
Here is the part of the cycle that most people forget. Once that steam passes through the turbine, it is still an incredibly hot gas. In order to keep the turbine spinning efficiently, you have to maintain a pressure differential.
Meaning you have to cool it back down.
Exactly. You have to rapidly cool that low-pressure steam back down into liquid water so it can be pumped back to the boiler and reused in the loop.
And to cool down massive amounts of steam, you need a massive external heat sink.
You need astronomical amounts of cooling water, which is almost always drawn directly from adjacent rivers, lakes, or oceans.
Wow.
The thermal power plant runs this cooling water through a condenser to absorb the heat from the steam. In the process, the cooling water itself becomes extremely hot. And guess what? A significant portion of it evaporates right there in the power plant's own cooling towers, or it is discharged back into the river at a much higher temperature.
So basically every single megawatt hour of electricity drawn from the grid by an AI data center carries a hidden, massive water debt from the power plant that generated it.
The water-energy nexus is completely inseparable. When an AI facility draws 100 megawatts of power continuously from a natural gas plant, it is indirectly responsible for the evaporation of millions of liters of water at that specific plant.
Okay, so we have the water physically evaporating at the data center to keep the silicon cool. We have the water evaporating at the power plant to generate the electricity to power the silicon. What could possibly be the third prong?
The creation of the silicon itself. The third prong is semiconductor manufacturing.
Making the chips.
Yes. Before a GPU ever gets installed in a server rack, it has to be birthed in a fabrication plant, a fab.
Yeah.
And the physical manufacturing of microchips is one of the most chemically and resource-intensive processes ever devised by human engineering.
Our sources emphasize that the fabs require something called ultra-pure water, or UPW.
Right.
What makes ultra-pure water different from, like, the filtered water I can get out of my fridge?
It is almost a different substance entirely. When we talk about modern GPUs, we were talking about transistors that are measured in nanometers.
Which is incredibly small.
To give you an idea, a single strand of human hair is roughly 80,000 to 100,000 nanometers wide. These transistors are single-digit nanometers.
Oh, wow.
So when you are using photolithography to etch patterns onto a silicon wafer at that microscopic scale, the environment has to be completely flawless.
Because even a single speck of dust would be like dropping a boulder on a highway.
Exactly. But it's not just dust in the air. It's the water they use to wash the wafers.
They wash them.
Yeah, throughout the lithography process, They apply chemicals, they etch the silicon, and then they have to wash the wafer perfectly clean before the next microscopic layer is applied.
Okay.
If the water they use to wash it contains a single microscopic trace mineral, I mean, literally a single ion of calcium, sodium, or magnesium, that ion will bond to the silicon and short-circuit the transistor.
Just one ion.
Just one. The chip becomes entirely useless.
So they have to strip the water of absolutely everything except pure hydrogen and oxygen.
They create water so pure that it actually becomes an aggressive solvent.
Wait, really? A solvent?
Yeah, it's starved of ion, so it will leach minerals out of anything it touches, which means it has to be transported in specialized polymer piping.
That is wild.
To create this UPW, municipal water is pushed through an agonizing filtration process. It goes through carbon filters, massive reverse osmosis membranes, ultraviolet light chambers to obliterate any organic bacteria, and finally, through ion exchange, resins that strip away the last remaining charged particles.
And the data shows just how punishing this filtration process is on the local water supply. To produce just 1 single liter of ultra-pure water, the fabrication plant can require up to 4 liters of regular fresh water.
Yeah, because the reverse osmosis and ion exchange processes generate a massive amount of rejected brine. As you force water through these microscopic membranes to get the pure water, all the impurities are concentrated into the remaining water.
Which I assume you can't use for anything else.
No, it becomes toxic and has to be treated and discarded. You are essentially throwing away 3 liters of water just to extract 1 pristine, perfect liter.
What's fascinating here is how water is intricately baked into every single layer of the AI life cycle. It is not an abstract byproduct, you know?
No, it's foundational.
From the intensive chemical washing of the microscopic silicon wafer in a fab in Taiwan, to the thermal exhaustion of the natural gas plant in Texas, to the daily evaporative breathing of the cooling towers in Arizona. I mean, water is the physical lifeblood of artificial intelligence.
If you look closely enough, you realize that artificial intelligence is simply the process of transmuting vast quantities of water and thermal energy into statistical probability models.
Wow. That is a staggering way to frame it, transmuting water into probability models. But, understanding the mechanisms, the how and the why AI uses water is only half the equation here.
Right.
To truly grasp the urgency of this deep dive, we need to zoom out. We need to look at the scale of current global consumption. Because we aren't talking about a niche experimental industry anymore.
No, absolutely not. We have crossed the threshold into macro-level planetary resource consumption.
Let's run through the aggregated statistics from the research. They calculate that the broader AI economy currently uses around 23 cubic kilometers of water per year.
I really want to pause on that unit of measurement because cubic kilometers are entirely outside the realm of human intuition.
Yeah, what does that even look like?
Imagine a cube of water where the width, the depth, and the height are each 1 full kilometer long.
Okay, that's massive.
Imagine 23 of those massive kilometer-high blocks of water. We are talking about tens of trillions of liters annually.
Tens of trillions. And if we isolate just the data centers, the reports show they consume hundreds of billions of liters globally.
Just for the cooling.
Right. And the aggregated data for the United States alone shows that U.S. data centers consumed roughly 66 billion liters in the year 2023. And a single hyperscale facility can drink 171 million liters annually.
It's just a colossal volume.
I have to stop and ask for a reality check here, though.
Oh, yeah.
We live in a heavily industrialized, globalized economy. We have massive chemical processing plants, paper mills, industrial agriculture, huge breweries churning out millions of gallons of beer. Is the tech sector's water use really that anomalous? Why is this specific usage from AI setting off so many alarms compared to traditional heady industry?
That is a highly critical question, and honestly, it is a point of major contention in environmental policy right now.
So what's the difference?
The alarm stems from 2 major factors. The first is the sheer velocity of the growth, which we will get to in a bit. But the second, and perhaps more immediate issue, is the specific type of water being consumed.
Okay.
AI data centers aren't generally drawing raw seawater or pulling from heavily polluted industrial wastewater channels. Our sources emphasize that they are overwhelmingly consuming high-quality fresh water.
You mean potable water, the exact same treated water that goes to residential neighborhoods?
In a vast majority of cases, yes.
Why do they need potable water just for cooling?
Well, the evaporative cooling systems, while not needing that crazy ultra-pure water like the chip fabs do, still require relatively clean treated water.
Because of the minerals.
Exactly. If you pump raw, mineral-heavy river water into a cooling tower, those minerals will rapidly precipitate out as the water evaporates. This causes severe scaling and calcification on the heat exchangers.
Which would ruin the equipment.
Right. To prevent their multi-million-dollar cooling systems from clogging up, data centers often tap directly into municipal water supplies.
So they are competing directly with the kitchen sinks of the local population. When a data center drinks 5 million gallons a day, that is 5 million gallons of drinking quality water that the local municipalities spent millions of dollars to treat, which is now no longer available to households or local farmers.
And because it relies on the exact same fresh water that human beings need to survive, the physical geographic location of these massive data centers becomes a high-stakes flashpoint.
Which brings us to the geography of this crisis, and frankly, the part of the research that baffled me the most.
It's pretty counterintuitive.
Right, we have to start with a baseline planetary reality. Fresh water is incredibly scarce. We call Earth the blue planet, but that's a really deceptive moniker.
Highly deceptive. I mean, while roughly 71% of the Earth's surface is covered in water, only about 2.5% of that is actually fresh water.
Only 2.5%.
Yeah. And of that tiny fraction, the vast majority is locked away in glaciers, ice caps, or incredibly deep, totally inaccessible aquifers.
So what's left for us?
The surface freshwater that humanity actually has access to, the rivers, the lakes, and the shallow groundwater that sustains all terrestrial life and agriculture, amounts to a fraction of a percent of the world's total water.
So usable freshwater is a finite, highly localized resource. Now, basic logic would dictate that if you are a massive tech conglomerate planning to build a facility that needs millions of gallons of water a day, you would scout locations next to massive, abundant water sources.
You'd think so.
You'd build next to the Great Lakes or in the Pacific Northwest where it rains constantly, but that isn't what is happening. The statistic from the reports is jarring. Around 40% of data centers are located in water-stressed regions.
It's wild. Almost half of the physical infrastructure of the cloud is being built in regions that are already facing severe hydrological deficits.
Let's look at the specific hotspots mentioned in the sources. Arizona, Texas, India, and the Middle East. Let's just think about the reality of those locations for a second.
Okay.
Arizona is in the middle of a historic mega drought, watching the Colorado River vanish. Texas's grid struggles with extreme heat and drought. India faces massive seasonal water scarcity and rapid groundwater depletion. The Middle East is a hyper-arid desert environment where water is arguably more precious than oil.
Right.
Why on earth would anyone build a massive, heat-generating, water-guzzling warehouse in the middle of a desert? It seems entirely counterintuitive.
From a purely ecological perspective, it is absolute madness.
Yeah.
But you have to remember, these facilities aren't mapped out by ecologists.
So who maps the map then?
They are mapped out by corporate real estate developers and infrastructure engineers who are looking strictly at profit margins and operational efficiency.
Follow the money.
Exactly. The sources point to several brutal economic drivers that just completely override the water scarcity issue. First, there's the cost of land. You can buy hundreds of acres of flat, easily developable land in the arid Southwest for a tiny fraction of what it would cost in a temperate coastal zone or near a major northern water basin.
But land is just a one-time capital expenditure. Surely the data to operational costs matter way more.
They do, and that brings us to the second and arguably most important driver: power availability and grid regulations.
Okay, how does that work?
Well, places like Texas, with its independent ERCOT grid, offer massive amounts of power, including vast new deployments of wind and solar. Furthermore, the energy market there is deregulated.
Meaning what for the tech companies?
Meaning tech companies can negotiate incredibly cheap, bulk power purchase agreements. Remember, these facilities are essentially giant electrical resistors. Electricity is their primary, overwhelming operational cost.
So they are prioritizing the electrical grid over the water basin.
They prioritize the electrical grid because electricity costs are immediate, they're volatile, and they heavily impact the quarterly balance sheet.
And what about water?
Water, conversely, is treated as an almost negligible line item. Because of the way municipal water is priced in many of these regions, it is heavily subsidized. It is a wildly underpriced utility.
Really? Even in a desert?
Even in a desert, a tech company can secure a contract for millions of gallons of municipal water at an industrial rate that barely even registers on their financial statements.
That is infuriating. And I assume the local governments in these dry areas are welcoming them with open arms.
Oh, yeah. Our sources indicate that local municipalities are often desperate for the economic development. They see a major tech company wanting to build a $2 billion facility, and they see property tax revenue, construction jobs, and, the prestige of hosting cutting-edge AI infrastructure,
So they just ignore the water issue.
basically. To secure that investment, local water boards or city councils will routinely fast-track permits, override environmental concerns, and absolutely guarantee the facility access to municipal water supplies.
Even if the local reservoirs are dropping to critical levels.
Even then, the economic incentive structure is completely decoupled from the ecological reality. If we connect this to the bigger picture, we're witnessing a direct collision course between corporate economic optimization, finding the cheapest land, the cheapest power, and the most favorable tax incentives crashing headlong into regional ecological survival.
And building these facilities in deserts isn't just an abstract anomaly for geographers to debate online. It triggers a cascade of devastating immediate ripple effects right there on the ground.
Real consequences for real people.
Exactly. Let's dig into the environmental and social fallout outlined in the reports. Because the physical environment does not negotiate with tax incentives.
No, the environment only responds to the laws of physics and the harsh reality of scarcity. The primary environmental impact detailed in the sources is straightforward depletion.
Depletion of the water tables.
Yeah. When a data center continuously draws millions of gallons from local rivers, groundwater aquifers, or municipal reservoirs, it physically alters the hydrology of the entire region.
What does that actually look like in practice for the people living there?
It means the water table literally drops. Wells that rural communities rely on start to run dry because the industrial pumps are pulling water out of the ground significantly faster than rainfall can recharge it.
Oh, wow.
It can even lead to subsidence, where the ground actually sinks because the aquifer below it has been emptied out.
The ground sinks. That's terrifying.
It happens. Furthermore, drawing down these resources drastically reduces the water available for local agriculture, which already operates on razor-thin margins.
And then there is the impact on the ecosystems themselves. The sources note that reduced water flows fundamentally damage aquatic ecosystems, wetlands, and wildlife habitats.
Everything is connected.
Right. I mean, if a river's volume is significantly reduced because a facility upstream is drinking it, the water temperature rises, dissolved oxygen drops, and the entire aquatic food web basically collapses.
And we cannot forget about what the data center puts back into the environment. The third environmental impact is pollution, specifically thermal and chemical pollution.
Chemical pollution from a data center? I thought they just evaporated clean water.
Not exactly.
Right.
We discussed how cooling towers work. As the pure water evaporates, the minerals and impurities in the remaining water become highly concentrated. To prevent algae, Legionella bacteria, and mineral scale from clogging the pipes, the facility has to pump chemical biocides and anti-scaling agents into the water.
It's like heavily chlorinating a public swimming pool.
Precisely. And eventually, that concentrated chemically treated water known as blowdown water has to be flushed out of the system.
And where does it go?
Well, this blowdown water is not only laden with chemical residues, but it is also physically hot. When this heated, treated water is discharged into local municipal wastewater systems or directly back into waterways, the thermal shock can be lethal to local fish populations and severely degrade the overall water quality.
And wrapping all of this together is what the sources identify as a devastating climate loop. It's a self-reinforcing cycle.
A vicious cycle.
Exactly. AI requires enormous compute. That compute requires massive energy. Generating that energy produces carbon emissions, which accelerates global warming. Global warming makes these already water-stressed regions even hotter and drier.
Right, and what happens when the ambient temperature outside the data center goes up?
The cooling towers have to work harder.
Exactly, meaning they have to evaporate even more water just to maintain the exact same server temperatures.
It is a textbook positive feedback loop leading to incredibly negative environmental outcomes. But the fallout isn't purely ecological, is it? The social impacts detailed in these reports are incredibly volatile.
They are. We really have to talk about the human element here.
Let's talk about it. The sources outline a rapidly growing social pension. You have these massive, multi-trillion-dollar tech companies directly competing for a life-sustaining resource with local communities that are already facing severe shortages.
It creates a profound structural inequality that is simply impossible to ignore. On one side of the fence, You have the most powerful, cash-rich corporations in human history. They have armies of lawyers, unlimited lobbying budgets, and immense political leverage.
They can buy whatever they want.
Exactly. If they need water, they will secure ironclad municipal contracts guaranteeing their access for decades.
And on the other side,
On the other side of the fence, you have local residents, small business owners, and generational farmers who are being told by the exact same local government that they must limit their water usage, let their crops go fallow, and take shorter showers just to conserve the town supply.
imagine the sheer resentment. I mean, you live in a rural town that has been suffering through a multi-year drought. The local well is drying up. The agricultural board tells you that you cannot irrigate your fields this season. And literally, right down the road, behind a security fence, a new tech facility is vaporizing millions of gallons of your town's water every single day.
Just so someone on the internet can ask a chatbot to write a poem.
Exactly. It's infuriating.
And this dynamic severely exacerbates the urban versus rural divide. These data centers are frequently built on the periphery of major cities to tap into the urban electrical grid and the fiber optic networks.
Right.
But by doing so, they drain the regional water basins that the surrounding rural communities desperately rely on for their livelihoods. It is quite literally an extraction of resources from the periphery to power the digital tools of the urban center.
It is a recipe for immense social conflict. The local impacts of these facilities are glaringly obvious to the people living right next to them. I mean, if a massive data center moves in and your community well runs dry, the causality is pretty clear.
You can see the cooling towers from your house.
Right. But here is the massive twist in our deep dive today, and arguably the most deceptive part of this entire industry. While that local impact is devastatingly visible, a massive portion of AI's water consumption remains entirely invisible to the broader public, and sometimes it even evades the scrutiny of regulators.
Yes.
The sources refer to this as the unseen footprint.
This is a vital piece of the puzzle because it completely reorients how we evaluate corporate sustainability reports.
Okay, how so?
Well, when a tech company publishes an environmental, social, and governance report, an ESG report, and boasts about their data center's water efficiency, they are almost exclusively citing their Scope 1, direct operational water use. They are only talking about the water physically flowing into the cooling towers on site.
The 5 million gallons a day figure.
Yes. But data from the reports fundamentally challenges this narrative. They highlight that the indirect water uses the water consumed in the supply chain to manufacture the GPUs, and critically, the water evaporated by the remote power plants generating their electricity frequently far exceed the direct water consumption of the facility itself.
Let me make sure I'm wrapping my head around this. If a major tech giant holds a press conference and announces, hey, we have engineered a brilliant new cooling system, and our new AI facility only uses 1 million gallons of water a day,
Right.
they might be telling the absolute truth about their on-site meters, but
Yeah.
they're completely ignoring the fact that the power plant 50 miles away is evaporating 3 million gallons of water a day just to keep their servers running.
Exactly.
And the fab in Taiwan used tens of millions of gallons of ultra-pure water to build the chips in the first place.
That is exactly the illusion. By compartmentalizing their reporting, they obscure the true cost. The supply chain hides the footprint.
It's so misleading.
It really is.
Yeah.
The water used to manufacture the hardware happens in one hemisphere, the water used to generate the electricity happens in another county, and the water used for direct cooling happens on site. But all of that water was consumed in service of that single AI data center's existence and operation.
Which means that whenever we read a headline about AI's water usage, we have to assume the true holistic footprint is vastly larger than the numbers being handed to the public.
Without a doubt.
And that brings us to a terrifying pivot point in the data. If the current footprint, which we know is vastly underreported, is already causing aquifer depletion and social friction today, what happens tomorrow?
That is the million-dollar question.
Right. What happens when generative AI goes from being a novel tool used by early adopters to being the fundamental operating system embedded in literally every digital interaction on Earth? Let's look at the future projections outlined in our sources because they describe an impending tsunami of demand.
The growth forecasts are where this issue transitions from a serious regional concern to a potential global crisis. The projected numbers are not linear. They are fiercely exponential.
Let me lay out the projections from the stack we have here. We have industry estimates projecting that data center water usage could reach 1,068 billion liters per year by 2028.
2028, that is barely a few years away.
Right. And looking slightly further out, the projections show that by 2050, global AI water consumption could exceed 54 cubic kilometers annually.
To put that 54 cubic kilometers in perspective, recall the 23 cubic kilometers we discussed earlier representing current usage.
Yeah.
We are projecting a 129% increase. It is more than doubling an already astronomical, planet-altering volume of water consumption.
And what exactly is driving this relentless exponential growth? It's not just people generating more pictures of cats, is it?
No, the novelty applications are just the absolute tip of the iceberg. The sources identify several massive structural growth drivers. First and foremost is the universal integration of generative AI across every sector of the global economy.
Like what?
We are talking about AI writing massive code bases for software companies, generating high-fidelity video for the entertainment industry, drafting complex legal documents, and synthesizing pharmaceutical research. It's going to be everywhere.
And I assume the computational difference between a standard web search and a generative AI prompt is pretty significant.
It is orders of magnitude different. When you do a traditional web search, the server is essentially just looking up an index file and retrieving it. It takes very little compute.
Just fetching a link.
Exactly. But when you ask a generative AI a question, it is not retrieving a file. It is running a massive neural network to calculate the probabilistic likelihood of the next word, generating original text from scratch in real time.
That sounds intense.
It is. The inference phase of AI, meaning the actual daily use of the model after it has been trained, requires staggering amounts of ongoing compute.
So every single time someone uses an AI assistant to summarize an email, a server somewhere has to run hot and a cooling tower has to evaporate water.
Yes, every single time.
What are the other drivers?
The rise of autonomous systems,
Mm-hmm.
self-driving cars, automated drone delivery networks, advanced robotics in manufacturing.
Oh, right.
These systems don't just use simple sensors. They process gigabytes of visual and spatial data per second, using deep learning models just to navigate safely. All of that data has to be continuously processed, updated, and trained in massive data centers.
And the sources also mention smart cities and the Internet of Things.
Yes, the IoT. When every traffic light, every power grid, every agricultural irrigation system, and every home appliance is connected to the internet and constantly optimized by predictive AI algorithms, the background compute requirement of human civilization becomes totally ubiquitous.
It's everywhere all the time.
Exactly. AI becomes the invisible, ubiquitous utility managing our lives.
Which means the water demand will be inescapable. But hold on, I have to go back to the efficiency argument for a second.
Sure.
The sources acknowledge that cooling technologies are getting better. The chips are getting better. If the tech gets, say, 50% more efficient at cooling, shouldn't that offset the growth in demand?
You are walking right into one of the most famous paradoxes in economics. The Jevons paradox.
Jevons paradox. What is that?
In the 19th century, William Stanley Jevons observed that as technological improvements increased the efficiency of coal use, the overall consumption of coal didn't drop. It skyrocketed
Aye.
because the increased efficiency made it cheaper and more profitable to use coal across vastly more industries.
Yeah, the efficiency paradox.
Exactly. The research highlights this chilling reality. A data center built today is undeniably more water efficient per megawatt of compute than one built 10 years ago. But because the technology is so useful, the sheer volume of global demand is growing so fast that it vastly outpaces any fractional efficiency gains. You might engineer a server that uses 20% less water, but if you deploy 10,000 times more of those servers across the globe, your total water consumption still explodes. The efficiency just enables a much larger scale of deployment.
Okay, here's where it gets really interesting. We have laid out a terrifying convergence of data so far. The physical mechanics of the heat, the geographical paradox of desert facilities, the hidden supply chain footprint, and these massive exponential growth projections.
That's a lot of bad news.
It is, but humanity is remarkably adept at engineering its way out of corners. The tech industry knows this is a bottleneck. Let's examine the solutions being proposed in the sources. Can we engineer our way out of this water crisis?
The sources outline several technological pathways, but it is critical that we evaluate them with clear eyes. Every single engineering solution proposed comes with severe limitations, exorbitant costs, or complex physical trade-offs.
So there's no silver bullet.
There is no magic bullet that suddenly makes AI impact-free.
Let's walk the listener through these options. The first one the sources heavily focus on is water recycling. The idea of reusing the water internally at the facility. I mean, why isn't every facility just doing this today?
Well, in theory, creating a closed-loop system is the ideal. You don't evaporate the water, you chill it and recirculate it. The limitation is the treatment process.
Treatment.
Even in a closed loop, the water absorbs impurities from the piping and the environment over time. To keep reusing it without fouling the delicate heat exchangers, you have to build advanced on-site water treatment plants.
Which I assume is expensive.
They require massive capital investment, rigorous maintenance, and most importantly, they consume a massive amount of electricity to run the filtration pumps.
So you are trading your water problem for a higher electricity problem, which, as we established earlier, just shifts the water consumption back to the remote power plant on the grid.
Precisely. You are playing a thermodynamic shell game.
The second proposed solution is shifting to non-potable water. Instead of drinking from the municipal supply that citizens use, companies could use treated wastewater from sewage plants or even seawater if they are located on a coast.
This is a highly promising approach from a social perspective because it immediately stops the direct competition with a community's drinking supply. And several major tech companies are actually actively retrofitting facilities to accept municipal wastewater right now.
That sounds like a win.
It is, but the engineering challenges are steep. Seawater, for instance, is aggressively corrosive. It will eat through standard pipes and pumps in a matter of months.
Oh, right, saltwater.
Yeah. And wastewater contains highly variable biological and chemical compounds that can foster massive bacterial growth in a warm cooling tower. To use these alternative sources, the facility requires much more robust, expensive, anti-corrosive infrastructure and heavy chemical pretreatment.
Okay, what about air cooling? The sources mention it, and it obviously uses no water. If water is such a liability, why don't we just mandate that all AI facilities use air cooling?
We touch back on the physics of heat transfer we discussed at the start. Water's specific heat capacity is just too valuable to ignore. If you mandate air cooling for a massive high-density AI cluster, you drastically lower the efficiency of the facility.
Because it can't keep up.
Right. The chips would have to be run at much slower speeds to prevent melting, and you would need cavernous amounts of physical space between the servers just for airflow.
Which completely defeats the purpose of high-density computing.
Exactly. Plus, the electricity required to run the massive industrial fans needed to move, that much air is staggering. Air cooling is viable for older, low-density traditional data centers, but it physically cannot handle the thermal load of next-generation AI hardware.
Then we get to the holy grail of current thermal engineering, liquid cooling. Specifically, things like direct-to-chip or immersion cooling. The sources highlight this as a highly efficient innovation. How is this different from the direct cooling we talked about earlier?
Earlier, we described using water to cool the air, which then cools the server, and evaporating that water to release the heat. Advanced liquid cooling skips the air entirely.
Okay.
In direct-to-chip cooling, microscopic microchannels of liquid are routed directly over the silicon processor itself. In immersion cooling, it gets even more extreme. You literally take the entire server rack and completely submerge it in a bath of specialized engineered fluid.
You dunk the entire computer in liquid. How does it not immediately short circuit?
Because they use the dielectric fluid. It is a synthetically engineered chemical liquid that conducts heat brilliantly, but does not conduct electricity at all.
Oh, wow.
The electronics operate perfectly while fully submerged. It is incredibly efficient. It captures almost 100% of the thermal energy without any evaporation loss whatsoever.
That sounds like the absolute solution. Why aren't we doing this everywhere today?
The immense cost and the complete lack of backwards compatibility. You cannot just take a billion-dollar data center built 3 years ago and fill the room with dielectric fluid.
Right, the buildings aren't designed for that.
It requires a total, fundamental redesign of the server architecture, the motherboards, and the building structural load-bearing capacity. Because tanks of fluid are incredibly heavy. It is the future, but transitioning the global infrastructure to immersion cooling will take decades and hundreds of billions of dollars.
The final and perhaps most brutally simple solution mentioned in the sources is better location planning. I mean, just stop building in deserts, build these massive data centers in water-rich, naturally cold regions like the Nordic countries, Iceland, or the Pacific Northwest. Let the freezing outside air do the cooling work for free.
It makes perfect, unassailable ecological sense, but it conflicts entirely with the economic and network realities of the internet.
Latency, right.
Yes. Data centers need to be relatively close to the population centers they serve to reduce latency, the millisecond delay it takes for data to travel through fiber optic cables. Furthermore, as we discussed, tech companies chase the cheapest electricity, the largest tax incentives, and the most deregulated power grids. Until the cost of water accurately reflects its ecological scarcity, corporations will continue to build in the desert because the spreadsheet tells them it is cheaper.
So we have all these isolated technological and logistical pieces, but our sources introduce a much broader systemic concept to tie all this together. They call it water circularity. What does that actually mean in practice?
Water circularity is a holistic, systemic approach to resource management. It forces a move away from the traditional linear take, make, dispose industrial model. A truly circular AI facility would approach water with multiple layers of responsibility.
Like what?
First, it maximizes efficiency, perhaps utilizing immersion cooling to minimize intake. Second, it aggressively treats and recycles whatever water it does use on site. But the third and most crucial step is active replenishment.
Replenishment, meaning the tech company has to physically put water back into the environment.
Or they fund massive hydrological projects that achieve the same net result. They might fund the restoration of local wetlands, repair leaking municipal water infrastructure that wastes millions of gallons, or subsidize advanced water-efficient drip irrigation systems for the farmers in the exact same basin they operate in.
Oh, I see.
The goal is to ensure that the facility's net impact on the local watershed is completely neutral, or, ideally, positive. It is a philosophy of balancing industrial growth with fundamental environmental health.
That sounds fantastic on paper. It sounds like the utopian solution we need. But as I look through the stack of research, a very hard, cynical truth emerges for me.
What's that?
Technology, immersion tanks, and lofty concepts like water circularity are just tools. A high-efficiency heat exchanger is just a tool. Tools do not wield themselves.
No, they don't.
They require human rules, human choices, and human enforcement, especially when utilizing those tools costs a corporation significantly more money up front than just draining a local aquifer.
And that transition is the absolute crux of the issue. We can engineer the most brilliantly efficient dielectric immersion cooling system in the world. But if it remains cheaper for a corporation to simply buy underpriced municipal water and evaporate it into the Arizona sky, the fundamental laws of free market capitalism dictate that they will choose the cheaper, more destructive option. Technology alone cannot solve an economic incentive problem.
Which brings us to the final and undoubtedly the most complex segment of our deep dive today: governance, ethics, and the moral dilemma. We are no longer talking about server architecture, latent heat, or supply chains. We are talking about human policy and societal values.
Because without stringent, enforceable regulation, tech companies are legally bound by market dynamics and fiduciary duty to prioritize rapid growth and shareholder returns over long-term planetary sustainability.
They basically have to maximize profit.
Yes, it is a classic tragedy of the commons. If the water is cheap, legally available, and the competition is using it to build faster AI, a company will take the water until the basin is dry. Relying on corporate goodwill is not a viable ecological strategy. Governments must intervene.
Our sources outline exactly what those necessary policy measures need to look like. First, governments must enact strict, scientifically backed water usage regulations. They need to cap how much freshwater industrial tech can draw from vulnerable basins, regardless of the economic promises made by the developers.
Furthermore, they need to enforce absolute transparency requirements. We discussed the illusion of the unseen footprint earlier. Regulators fundamentally cannot manage what they cannot accurately measure.
Right?
Tech companies must be legally mandated to report their comprehensive end-to-end water footprint. That means disclosing not just the on-site evaporation, but the Scope 2 water used by their power providers and the Scope 3 water embedded in their hardware supply chain.
The sources also suggest mandatory environmental impact assessments that specifically analyze hydrological stress before ground is ever broken on a new data center.
Which should be standard practice.
Yeah, exactly. And to be fair to the industry, regulators should offer aggressive financial incentives like tax breaks, massive subsidies, or expedited permitting for companies that genuinely deploy sustainable, water-neutral tech, like wastewater recycling or liquid immersion.
The regulatory framework has to artificially shift the economic calculus. It has to make sustainability significantly cheaper and more profitable than ecological exploitation.
But beneath the regulations, beneath the policy white papers, I want you, the listener, to ponder the deep ethical questions raised by these sources. This isn't just a spreadsheet problem to be solved by optimizing variables. It is a profoundly human problem regarding how we value resources.
It really is.
Ask yourself, should a technology company driven entirely by profit motives be allowed to consume the drinking water of a drought-stricken community. When a regional reservoir is dropping to critical levels, who gets priority? The local agriculture that feeds us or the data center that powers a search algorithm?
It's a tough question.
Is the convenience of an instantaneous AI assistant or the ability to generate a funny image truly worth the environmental cost of a dried-up river? Who gets to make that decision?
This raises an important question, perhaps the ultimate question, this entire analysis. We are standing at a definitive fork in the road right now. Our sources clearly outline two diverging paths for our immediate future, and the clock is ticking rapidly toward that massive 2050 demand projection.
Let's examine those two scenarios. Scenario one, as presented in the text, is the crisis scenario.
In the crisis scenario, humanity continues business as usual. We prioritize unrestricted, unregulated AI expansion because the economic gains are just too tempting to slow down.
And what's the result?
The result is rapidly increasing water shortages worldwide. As hyperscale data centers drain local water tables, intense social conflicts erupt. Rural communities protest, regional agriculture fails due to lack of irrigation, and vulnerable aquatic ecosystems degrade beyond the point of repair.
Wow.
We achieve an astonishing technological leap forward in artificial intelligence, but it results in a devastating ecological step backward for the physical planet.
It is a remarkably dark vision of the future. But scenario two is what the sources call the sustainable transformation.
In the sustainable transformation, we face the physical reality of the technology head-on. Governments implement strict, transparent regulations. Data centers are legally mandated to use highly efficient cooling technologies and renewable energy sources. Water recycling and circularity are implemented at scale across the entire industry.
We basically force the industry to adapt.
Yes, we build a culture of responsible AI development. And the research notes an incredibly optimistic twist in this scenario if we manage this transition responsibly. The immense, unparalleled computational power of the AI itself could be deployed to analyze, optimize, and better manage global water distribution systems.
Oh, that's interesting.
Yeah, the very technology causing the strain could become the ultimate tool for solving planetary resource management.
So what does this all mean? We have covered a massive amount of ground today. Let's synthesize this journey. Artificial intelligence is fundamentally, irrevocably reshaping the architecture of human civilization.
Absolutely.
But it is not magic. It is not a weightless cloud. It is deeply, inextricably tethered to the physical world, bound by the unforgiving laws of thermodynamics. And it is rapidly becoming one of the largest industrial consumers of our most precious, finite resource, fresh water.
The core issue isn't just the staggering volume of water being consumed, though those numbers are absolutely terrifying. It is the context of that consumption. It is the geographic paradox of building massive heat engines in the middle of dying deserts. It is the unseen footprint hidden within complex global supply chains and distant power plants. And it is the harsh, immediate reality of pitting corporate technological progress against the basic survival needs of local communities.
It means we are at a crossroads. We can blindly expand, marveling at the neat tricks our computers can do while willingly walking into a global water crisis. Or we can force the tech industry, through rigorous regulation, economic incentives, and public pressure, to develop a sustainable AI ecosystem. We want the future of AI to be brilliant and transformative, but it has to be responsible.
It must respect the absolute physical limits of the planet because silicon, no matter how intelligently it is arranged, simply cannot compute without water.
I want to leave you with a final thought, something to really mull over the next time you pull out your phone. Open up that app, type in a prompt, and wait for the artificial intelligence to answer your question.
Keep in mind,
if we don't force a change in course, if we don't demand absolute transparency and systemic water circularity from the companies building this future, we might find ourselves living in a tragic, catastrophic irony. An irony where humanity successfully builds an all-knowing, super-intelligent AI. We ask it how to solve the global climate and water crisis, only to realize it just drained our last remaining reservoir to compute the answer. Think about that the next time you look up at the cloud.